continue to prove Bertrand's postulate, but I want you to clarify some definitions regarding the statements involved in this proof. So I first want to tell you about suppose we have a prime number p and a natural number n. So the largest power of p which divides n, that is a prime power, right? We call it as p power r. So this p power r will divide n, but p power r plus 1 does not divide n. So this p power r is called the largest power of p which divides n. And this r is called the index of largest power. Okay, right. So in Legendre's theorem, what we have found a formula for index of the largest power which divides n factorial, right? So r p power r divides n factorial, but p power r plus 1 does not divide, right? And we have seen that a prime, the index of largest power of a prime p is the maximum of r such that p power r less than or equal to 2n, right? So what that means, the largest power of p dividing 2n cn cannot be greater than 2n. It's not larger than 2n, right? So largest power of p divides 2n cn is always less than or equal to 2n, because the index is defined like this, r such that p power r is equal to 2. So that's what we have proved. Now we come to a very major argument which is in Erdos proof, that primes between 2 by 3n and n will not divide 2n cn, right? So that's idea. So here is our claim: primes p that satisfy the inequality 2 by 3n less than p less than or equal to n, they do not divide the binomial coefficient 2n cn at all. Now we need this. How do we prove this? So this is very easy. If 2 by 3 times n less than p, that implies 3 times p greater than 2n. That means in 2n factorial there is only 2 factors of p, that is p and 2p, because after that it is 3p is coming, 3p which is greater than 2n, which will not contain in 2n factorial as a factor, right? Yeah. So these are some examples that you can see 2n where p and 2p are present. So what we can see that p and 2p are the only multiples of p that appears as a factors in the numerator of 2n cn, that is 2n factorial by n factorial times n factorial. So in 2n factorial p and 2p are there, but in the denominator there are 2 factors of n factorial. So n factorial also contains p. Why? Because p is less than or equal to n, right? So n factorial contains p as a factor, so 2 of them, so this p cancels out. So in short, the primes between 2 by 3 n and n will not contain and they will not divide, okay, in 2n cn. They are not there actually. Okay, so they do not divide 2n cn at all. Okay, so that's the idea, because they are not a factors. If p is a factor, then only they can divide, right? Because it is a prime number, right? Now yes, Now we are ready to estimate 2n Cn. So basically we are going to find a lower bound. So in order to see that, we have to look at an estimate. So we start from a well-known formula, identity actually, nc0 plus nc1 plus ncn up to ncn is 2 raised to n. So the proof of this is very easy. If you recall the number of elements in the power set of a set with n elements, this is going to be 2 raised to n. So counting this, we see how would you count it? First you have one element set, so nc1 of them, and you add two element set, nc2 of them. Finally you have ncn of them, and also you count nothing, nc0. So that is equal to 2 raised to n. So you're starting from nc0, right? Okay, one element set, okay, and also you add empty set, so nc0 is nothing, 1. So that comes the formula like this. Okay, in this formula the first and last fellows are 1, nc0 and ncn are 1. So I just coupled together, it is 2, and from here onwards nc1 plus up to ncn minus 1, just rearrange it, equal to 2 raised to n. Now note that what is the maximum value of nck? So this can be found from Pascal's triangle. So I just recall Pascal's triangle quickly. So Pascal's triangles describes the binomial coefficients, right? So I want to describe like this: 2 power 0, right? So just that is equal to 1, and 2 power 1, that is 2. So this is you are getting because 2 0 plus 2 1. Similarly, this one is 2 power 3. This is as the sum, you get 3 0, 3 choose 0, 3 choose 1, 3 choose like that. So you can see that the maximum is 3, right? So it comes in the middle, and when n is even, then the maximum comes in exactly in the middle. So ncn by 2. Look at this: 4z0, 4z1, 4z2, 4z3. So 4z is going to be 6. So in generally we are getting this upper bound and inequality, which is nck is less than or equal to nc floor of n by 2 for all k less than or equal to n. Now I use this inequality 2 raised to n, which is less than or equal to, I replace all these sum n's by ncn by 2. 2 is less than or equal to nc and floor ncn floor n by 2, then all of these things. So how many terms are there? 1, 2, already n minus 1 of this, and 2 including this n elements. So n times I am getting nc floor n by 2. And if you rewrite this 2 raised to n less than or equal to n times n choose floor n by 2, and finally you get this. So you get this 2 raised to n over n less than or equal to nc floor n c by 2, and you replace n by 2n, then you get this estimate 4 raised to n over 2n less than or equal to 2n choose n. Okay, so that is the estimate we wanted. Now we come to, next we are going to find an inequality using this, and from that we will end up a contradiction, right? So yeah, so I'll give you an idea about this. So we have found that this is true for raised to n over 2 when less than or equal to 2n cn, and not this one. It is equal to, so any number can be as a prime factorization. Any number can be written as like this, some pk rk, right? Similarly, we can also write 2n Cn. 2n Cn has also a prime factorization. That is, it is the product of primes, right? P power Rp, the index is depends on. So Rp is the largest index of the largest power of P, right? And also note that 2n Cn contains only primes less than or equal to 2n. That's very important. That means even if you have n factorial contains primes less than n. Why? Suppose you have a prime greater than n and that divides n factorial. And you know prime divides n factorial is 1, 2 up to n. You have a prime has a property. If prime divides a product, it has to divide at least one of them. So prime divides one of this number I varies over 1 to n. But that is not true. Because all these numbers, by divisibility implies p less than or equal to I. But I is less than n. So the inequality is completely reversed. P less than n. But we have p greater than n. So because of that, every prime which divides n factorial should be less than or equal to n. So similarly, you replace 2n. So in the prime factorization of 2n factorial, there is only primes will be less than or equal to n. So it can be expressed like this. And 2n Cn is just divided by 2n factorial divided by n factorial 2 times. So no problem, right? So now I can estimate this. Now we can estimate this is very easily. 2 arguments will follow. Now first thing, I will split the product. Okay, first I'll split the product like this. I also split like this. Then I will change. Now it is an equality. First you have to note that when I split, I split the primes in this fashion: p less than or equal to root 2n, root 2n less than p less than or equal to 2 by 3n, and n less than p less than or equal to 2n. There are 2 questions. A product is missing, that is 2 by 3n less than p less than or equal to n. That product is missing. Why it is missing? Because we already seen that there are no primes which divides 2n Cn. That's what the argument says. So there is no prime, so the product is empty. So I don't want to showcase that empty product. So it is 1. Empty product is 1. Now the thing is it always true that root 2n is less than 2 by 3n? It is not true always. It is only true when n greater than or equal to 5. That you can start from when n greater than or equal to 5, 18 minus 4n is less than 0, because when you give n equal to 5 you will get negative 2. Then when you increase the value, this is also negative, and if you multiply with the positive integer still, and from this argument n times 18 minus 4n less than 0, you can end up with this. But that is only when n less greater than or equal to 5. But we only need sufficiently large n, so we can do this. This splitting is valid. That's what I am telling. P less than or equal to root 10 less than p less than or equal to 2 by 3n. Then we missing the empty product. Then n less than p less than or equal to 2n. So the product. Now I want to tell. I have the first product. Look at the first product. The first product is p power rp. Right? A prime in raised to the index of the largest power. Right? Now we already seen that whenever a prime divides 2n Cn, it's that prime power will not be not larger than 2n. That we already seen, right? So a prime power is not larger than 2n, or whether the prime divides 2n Cn, the prime power, the largest power of prime is not larger than 2n. So that means all of this quantity is less than or equal to 2n. So I can replace all these prime powers by 2n. So it is less than or equal to that. Now this Rp is going to be 1. Why? Because whenever primes are greater than root 2n, we have found that its power should not be its index should not be greater than 1, because if it is p square, what happens? Then p square is greater than 2n. That's not possible, because every prime power should be less than or equal to 2n. So this means this is 1. Similar, that is the same case, because this prime is also greater than 2n, so this is also 1. So finally we get this, right? Yeah, this is not needed anyway. Okay, RP is 1. Now here in 2n there are how many primes will come maximally? So there are not more than root 2n primes which are less than or equal to root 2n, of course. There are root 2n primes. So I'll replace that, and the product will be, turns out to be, this is basically root 2n, then there is a 2n, right? So it goes there, then it makes 1 plus root n, and these things are there, right? Yeah. Okay, so this is the setting. So we are getting up to this, and next we prove that next it comes the climax of the theorem. So what we have seen is, we have proved that 4 raised to n is less than or equal to 2n raised to 1 plus root 2n, product root 2n to root 3n, product p, n less than p less than or equal to n. Okay, so now wait for the climax. Next part we will finish Bertrand's postulate. Thank you.